and welcome. I'm Philipp Meyer. I'm collecting vintage computers and vintage technology. And one common problem you always have is when you get a new device, you want to make sure that your firmware ROMs are securely backed up. And yeah, this can sometimes be a problem because the modern programmers, they won't have support for these very old ROMs. And yeah, and I've come up with a solution I will show you in this video, and I will also show you how I dump the firmware of my vintage HP21MX CPU. So, believe it or not, this is the CPU I mentioned. It's of course not an integrated circuit like CPUs we have today, or like CPUs which were common in the late 80s and 90s. Yeah, this is entirely made out of TTL ICs. And here in the back you see the 21MX computer where the CPU would go. It would go in the bottom there. And yeah, from this CPU I want to dump the microcode and the firmware. These CPUs were quite feature-rich back in the days. Yeah, the 21MX came out at about, I think it was 1976, and I believe this particular CPU model is from 1984. They made them pretty long. It was a pretty long-lived architecture, but when I look here at the, let's see if we can spot some date codes here. It's yeah, I see 84 there, 83, this 84, oops, where I'm at here, 84 again, and also these ceramics here also have a date code as well. Can read something like 84 as well there, 13th week 84 presumably. So this is not a super old CPU, so it's quite remarkable that in 84 you would get a CPU that is still entirely made out of TTL ICs. But as I said, it's a very long-lived architecture, and so they made them. They did a lot of production runs of this because these things were used in critical infrastructures and in probably very expensive machinery, and so there was presumably there was a demand for a long time. I don't know when they phased it out, but it was very long lived. And yeah, as I said, it doesn't look like, but it's very feature rich. This CPU comes with integrated firmware ROMs, so we can see them here. They're not as the EEPROMs in more modern machines, so these are actually 4-bit PROMs. So the chip inside it consists basically of a diode array and the programming device that just burns diodes away. So that's not like in an EEPROM with the floating gate, and it's really burned in there. So if we would open one of these, I think under the microscope you should see the burns. Yeah, these are 4-bit ROMs, and it's a 16-bit machine, so they do some tricks to basically one word is read in 4 cycles, and this is a bit tricky. So we see 4 slots here, but it's not like they're doing them in parallel. So one ROM contains one firmware, and if you look at 4 consecutive addresses, you see 1 instructions. I have some of the firmware already downloaded from the internet, so other people also did some ROM dumps and I compared it. So I can confirm that my readout works. Yeah, so this is in this section here. They are you can change them. So depending on the boot device you have, you would insert another firmware. It's not like on the modern PC where you have a BIOS that does all the tricks and has all the drivers for all possible IDE drives and drive layouts and stuff. So for each drive, whether it's a tape drive or disk drive or whatever, you would set up the appropriate boot ROMs here. And there are also tests which I believe are in here. So this machine does, on boot up, it does a RAM test, so it tests itself. Maybe there are also a couple of more tests you can select with these switches, I don't know. Didn't come very far yet with this. But yeah, these testing software is presumably in here. And these are normally not in sockets, so I undone the ICs and put them in sockets because I want to have full access on that. And probably hack around this, because these, of course, you won't get them anymore, but you could easily make an emulator out of an EEPROM or something with some glue logic around it, or probably you don't even need that. And now we have these bigger ROMs here and these 3 free slots. This is the microcode. So this is what makes the CPU tick. This is actually a microcoded architecture. You wouldn't expect that from a CPU that is entirely made out of TTL-ECs. I thought that microcoded architecture would be far more complex. But yes, it's microcode, and the microcode is stored in these 3 ROMs here. And this is also upgradable. You could add microcode on demand on this, or if there are microcode upgrades, you could upgrade it. And this is also in sockets, so if you have CPU bugs, you could fix them like this. Yeah, this is also one-time programmable stuff. And this machine also has the ability, if you had the right accessories, you could attach a RAM. And this RAM would be basically a microcode control storage. So you could basically runtime upgrade the microcode of your CPU depending on what applications you run. You could basically enhance your CPU on runtime and accelerate, basically load Fortran accelerations. And if you wouldn't go for that, you could also acquire from HP microcode accessories which would attach here through a cable, and these were also ROMs. I have boards that are about this size, which are full of microcode accessory upgrades. I don't know what it really is. We'll presumably do some research later, but for now we will focus on the CPU and dump everything that's on it. We will dump the microcode and the firmware. And yes, of course, we need to do these labels to see what it really is. And this thing here lists as N8255181F, as I can see. I already took the notes. And yeah, here we have one other one. You found out these firmware ROMs. I'm presuming these are all the same. And this lists 18160782. This is of course not the real manufacturer's part numbers. This is the HP internal stock numbers. So as you can see, all these have these numbers. I mentioned it in a previous video as well. So they also have these 8-digit numbers, which is the internal stock number. Some of them do not even list the real TTL, SN, whatever number. So you have to look into cross-reference to really know which part it is. So that's what we will do next. So the N82S181 was easy because that didn't have the HP internal stock number. So that basically gives us the data we need. So it says it's field programmable, and yeah, some data input loading stuff, full TTL compatible. I'm actually glad that this stuff I have here from HP is a TTL machine. ECL would be presumably much more complicated. And this is how it works. Chip select inputs and stuff. Pipeline prompts. So it's not all that interesting for me. In particular interesting is the pin out. That's basically all I need to dump it. So yeah, let's see what the firmware ROMs here, the 18.16.07.82 have. So from the good old days I have these bench briefs, service information from Hewlett Packard. It's actually also quite recent, it's from 1990. Let's see if we can find our ROM. It has some explanations at the beginning. Oopsie doopsie, let's see where get it. That's of course all the interesting to read, but for now, boring stuff. Whoops. Here we have it. Here it comes. So we have a 1816. That must be around here somewhere. 82. There it is. 1810782. There, so 1810782, and it's an HM76115. So let's see what we can do about that. Yeah, well, unfortunately I wasn't able to get smart out of this part number, so I pulled out another cross-reference, and this one lists these part as a N820S1 N82S129F or I21F. Yeah, this is the integrated circuit cross-reference from somewhere. I don't remember who made this, but presumably this is not HP, this is some third-party stuff. Good, anyway, I pulled out the data sheet here. This is from, yeah, surprise, surprise, Signetics. HP used a lot of Signetics back then. And yeah, here it is. So this is the pinout of the IC, and yeah, and I get it on a nice yellow scanned data sheet. So no post-processing done on this data sheet. Very neat. They also come with an example programmer circuit here. Okay, anyway. What do we get here? The N82S126 open collector outputs, by the way. You need pull-ups. And yeah, 3 set outputs bipolar. Yeah, and yeah, the address goes in here, and here we have the outputs for, of course. So now we got everything we need. We know our parts, so let's think how we can read them out. So it's the equipment I normally use to dump ROM contents. So yeah, most of the time I use my Garlab. This is the one I had first, and I kind of like this thing. So it's a really yeah, I got used to it anyway. So I also bought some years ago a Bachonics BX84, but since it let me down at one EEPROM dumping session out in the field, I kind of got reluctant to use it. But it's also a very nice device, so very well done, and I think it's better for more modern ROM parts. And yeah, I have these adapter sockets, so I had to dump, back in the days I had to dump some more modern stuff, so I used that. Yeah, but this is really good at EEPROMs, so I use it a lot. And yeah, both of them come with a special service, so you can send your part in and get basically support for your part for free. But I kind of do not feel very comfortable to send ROMs in that are that old and that particular have a value for me. So basically this is done for, I mean, if you basically engineer something new and you send a sample in and you don't expect it to see it again anyway. So, and it's, yeah, basically some new part you want to use, and your reader doesn't have the support, then they will do it for you. But for vintage stuff, not really useful. Yeah, these have very broad support, very lists with tons and tons of parts. But in my case here, these parts are just too old. They are not supported by this, so no chance with that too. So I came up with my own little reader. So this is not able to program ROMs, it's read-only. But that's just what I need, flexible circuits that I can use to read ROMs. I call it the chip helper. Basically, it's a very, very simple device. It consists of an 18 mega 128 processor. I chose that one because it has a lot of I/O, and basically all these I/O pins they run to the SIF socket, and I have jumpers here so I can connect and disconnect pins from the microcontroller as I want. And I also have power cables, so actually try to use the I/O pins as a supply, but that doesn't work. These old parts just draw way more power than one I/O pin can deliver. So you really need these externals. So that's there's also where the jumpers come in handy. I can just pull them and replace them with power and ground on both sides, just to be more practical. And yeah, this works out. And as I have full control of the firmware inside there, I can add support as I like. And I will also show you how the support for these particular two chips, at least for one of them, how that would look like in the code. So this is open source. You can download it from my webpage as usual, and maybe it's useful for you and you have the same problem like I have, and you could basically add support for your part easily. Yeah, and there's also something I had recently. I had to repair an old terminal, and yeah, some of these, one of these TTL IC got bad, and I didn't know which one, so I checked them one by one. I needed a tester, and so this also acts as a tester. It has some testing functions in the firmware. You can run sort of a unit test on TTL ICs. And yeah, I mean, at the moment it supports only a handful of parts, in particular the parts I had to test or dump. But yeah, same here, you can add support on the go as you need. Yeah, so let's do some ROM dumping and have a look at the firmware in particular. So what we're looking at here is the firmware code for the support of the N82S126, 129. This is the smaller ROMs you have seen in the beginning of the video, and here I usually start to make up a map for myself so that I see where's VCC and where's ground and where the address is going in, where the data is coming out, so I that I have it on screen. And then the firmware is made up in a way so that you just define a table in the program of the MCU, and there you just list the pins which are responsible for the address. So in our case this is 567 A0, A1, A2. You can follow that. So then it goes again with A3, A4, A56. It's then on pin 4, 3, 2, 1. And the 39, that is the A7. So basically this is basically a vector-like description of what you see here. And Then we have two functions in this code. We have an init function. I usually used to call them here dumper underscore the name of the part and then init. So this is consistent about throughout the firmware. So like kind of a convention here. And yeah, target is the target I want to read. And the first what I do is I initialize that with the values I need for the remaining pins. So as you have seen, there's chip select and stuff. I need to initialize as well. So that's what I am doing in the init function. So that is then set to basically fixed values. So I have here value 0 and value h. So it's these 33, 34, 36. They are set to high. Let's see what that is. Yeah, this is the address. So this is basically the pull up. So it's basically weak high. So the H and this stuff is consistent to what you have in VHDL. You have the 0, I think, and runs and H, and let's see what we can have here. So yeah, here we have it. So we have 0 and 1, that is basically hard, hard low, hard high. So basically it's actually driving. So then we have just high impedance without pull-ups at Z, and H, this is weak 1, high impedance, basically pull-ups enabled. So just that, so this enables our pull-ups because we may have open collector outputs on this ROM. And then we drive the chip select line slow to select the chips. So that's basically it here. The other pins do not need initialization. They are initialized on the fly when I do the target write and the target read. Basically after the reset they are of course always input. And yeah, here I do target write. And here I feel the address map as the map address, which the vector we defined before, we defined above here. So this is the map address and map data. And when we use this function, it cares about all the pin mapping and stuff. We just give it the address here that comes in by it's basically a counter defined above. Here we have 2 and 16 address, which is initialized to 0 on the init function, and then basically we do a write to that address, and then we could do a target read, which gives us back the byte, and we also give it the map, so it actually already knows, the read function already knows where the pins are mapped by giving it the map. And you basically don't have to do all this port initialization, all the stuff again. You just define the map and that's it. And yeah, it's not, stuff is not very, so there's no luxury we have here. It's just, oops, let me minimize that. So it's just, I mean, it's not too smart here. We have a jump table here, which all jumps to all these initialization functions for the parts we have. And then we have here, depending on which device ID is selected through the software, so we have a command line tools for Linux that basically sends a device ID and tells it to read. And then you have this jump table here. That's basically it. And you basically would have to write your own file in that fashion and add it here to the jump table. That's basically it. It's pretty straightforward, and I mean I had to roll it on the chip, and it had to be made fast, as due to the lack of time I'm always suffering from. So I mean it's simple, and it's I mean anybody could extend it. No advanced skills required, so to say. So now enough with serializing everything. I think it's now really time to for the fun part to actually dump the ROMs. Okay, I've set it up now. Yeah, this is how it's done. I've connected the VCC to the right uppermost pin, like the datasheet also suggests. Here you can see VCC that's there, and the ground is there, so I have put it here as well. So the rest is done programmatic. So it's connected to the USB, and I have the command line tool. The command line tool, by the way, doesn't require it to be touched if new support for new parts is added. So you have need only to touch the firmware. So, and it can list all the parts. Of course, we have to give it an USB port then, because the list comes from the firmware. So, and here we have a selection. At the moment, 5 parts only. And yeah, we need the number 2, that's the N2 is 126, 129, like we have here. So yeah, now let's dump the part. So here we have it. I already prepared that a bit. It's the 8004 12992. And these ROM was in the socket U196. So now let's go. And that's it. Here we have it. Fits on one screen. This thing has only 256 address, so that's it. Since we only have 4-bit words in that ROM, of course the first nibble here in these hex dump is always 0, and that is also consistent to the format I found on the internet. So, and I'm pretty sure if we would concatenate this to a 16-bit word, and we would look in the original binary dumps I already have, or in the assembler dumps in the manuals, I'm sure we would find the same there as well. Okay, yeah, that's all it is for the dumping. And yeah, now let's do the big ROMs next. Yeah, and let's now take on the microcode ROMs. I have one here. Same procedure, same setup. VCC and ground. And yeah, let's go. Oops. Wasn't quite right. I forgot to remove the list switch. So now, here we have it. That's part of our microcode. And yeah, of course, this time it's 8-bit words for the ROM. Yeah, as you can see, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So yeah, that's it. So now we have dumped the microcode, at least 1/3 of it. And yeah, I will do the other ROMs off camera, of course, because it would be too long then. But yeah, that's basically how it's done, how you dump exotic old ROM memories. So that was it, and I hope you found my video helpful and enjoyable, of course. So yeah, see you next time. Take care. Bye bye.